Okay, here's a couple more slides, hopefully getting to the end of the presentation on modulation bandwidths and rate distance products. So what I'm going to do now is we're going to go ahead and look at a couple of different modulation formats, and we're going to see what their spectra look like in the electrical world and use that to help figure out what the bandwidths of or what the maximum data rates are going to be depending on the type of modulation. We've got two different types of modulations that we'll use in our fiber optic systems. The first one is sort of what we've been working with in our sort of cartoon pictures all along. The first one is NRZ, non-return to zero. And the other one is RZ, which is return to zero. And in the NRZ case, what we'll do is we'll have, as a function of time, a voltage signal that goes, as I say, exactly the way we've been plotting it, with a 1, 0, 1 giving us a little square wave here, where the bit period then is, as shown here, TB. Okay? This is the NRZ case. In the RZ case, our voltage as a function of time is going to return to zero in every bit period. So I'll draw my same 3 bit periods here, and I'll draw the 1, but the waveform always returns to 0 right in the middle of the bit period. And so 2 1 pulses, 2 1s, a 1, 0, 1 looks like 2 pulses, but they're of half the duration. And in fact, their duration is half of a bit period. And so if I have all 1s in the RZ case, I'm going to have, let's make a few 1s in the RZ case, then I'm going to have essentially what looks like a square wave at twice the bit period. In other words, the spectrum occupied by the RZ signal is twice as wide as the spectrum occupied by the NRZ signal. So here are the bit period boundaries in this picture. Okay, so you can see that the highest frequency sort of square wave I can get in the NRZ case is equal to 1 over the bit period, whereas here it's twice. And we can then quantify that by making little plots of the electrical power as a function of frequency, essentially a curve showing the frequency content of the signals. And what I'm going to do is I'm going to make one for the NRZ case and one for the RZ case. And in each one, I'm going to write 1 over the bit period as sort of the baseline frequency that I'm going to look at. And so the NRZ case is going to have a maximum frequency more or less equal to 1 over the bit period. And so this spectral content plot is going to sort of die off very rapidly and almost essentially go to 0 at 1 over the bit period. Okay? And we can then characterize this. Well, you know, when our electrical power goes down as a function of frequency, this is that Gaussian that I drew before. And so at the halfway mark, more or less, I can write 1 over 2 TB at half that point, more or less writing F3 dB electrical is 1 over 2 T bit. The spectral plot for the RZ case, however, goes all the way out to 2 over the bit period, and so it's much wider. And it turns out that the 3 dB electrical bandwidth for this case is different. It's about equal to 1 over the bit period. Okay, so the RZ signal has a wider bandwidth because of the faster modulation, the maximum modulation that can happen. Okay, and so these two equations are going to be where we start on the next slide. So what we're going to do is we're going to start with the equation that I showed earlier a couple slides ago, which was, let me find it. Here it is. I sort of said for a fiber optic system, if you recall this slide, for a fiber optic system, this 3 dB optical bandwidth is, let me use the slide I had made for this. Sorry. Here we go. That this 3 dB optical bandwidth was 1 over 2 delta tau. So this was our slide that talked about the optical bandwidth from the beginning. And so I'm going to start with F 3 dB optical is 1 over 2 delta tau, where delta tau is my pulse spreading. From that, we can derive that F 3 dB electrical is 1 over the square root of 2 times that value. That's something we derived in the last slide, in the last video. Conversion between electrical and optical bandwidths. And so this is then essentially 0.35 over delta tau. Okay, so this was a 0.5 over delta tau. And 1 over the square root of 2 is 0.707. 0.7 times 0.5 is 0.35. So that's where this equation comes from. We can now combine these with the data rates for NRZ and RZ. We can write that the data rate for the NRZ is 1 over the bit period. Okay? And this is then twice F 3 dB in the electrical domain. Okay? And that comes from this graph right here, showing that the 3 dB electrical bandwidth is twice that is 1 over the bit period. Okay? And so this is now, let's see, the 3 dB electrical bandwidth is the optical bandwidth divided by the square root of 2. So I have 2 over the square root of 2, F 3 dB optical. Okay, and so this is finally the square root, 2 over the square root of 2 is just the square root of 2, and this 3 dB optical is 0.5 over delta tau. So the square root of 2 well, one way or the other, this comes out to be 0.707 over delta tau. Let's see, 3 dB optical is 0.5 over delta tau. The 0.5 times the 2 cancel, and I get a 1 over square root of 2, which is 0.707. There we are. So I get the maximum NRZ data rate is 0.707 divided by the pulse spreading. I can do the same calculation for the RZ rate. And the rate for the RZ is 1 over its bit period, but that is equal to the actual 3 dB electrical bandwidth. Again, we go back here now to look at the RZ plot, and 1 over TB is equal to the 3 dB electrical bandwidth. And so it's just half of the values in the above equation. And so this is 0.35 over delta tau. Okay? And so I'm finally rounding out the equations given in chapter 3 on this topic. And so finally I can write in terms of pulse spreading per unit lengths, I can write R NRZ times L is equal to 0.707 over delta tau by L. Here I've essentially just multiplied both sides of the equation by L, and we can also write that R, the data rate for RZ times L, that is the rate distance product, is 0.NRZ, 0.707, right? And this one is 0.35 all over delta tau by L. Okay, so these are the two equations that we've been trying to get to, and hopefully this sort of schematic picture of the data rates is convincing to you, and that these equations are now something you can use in your calculations to do problems in Chapter 3. Thanks.